All right, welcome to the second video for chapter 5. We're going to be talking about normal distributions. Normal distribution is the classic bell-shaped curve. And so there's an app online that can show you what a normal distribution looks like. And it looks like a bell-shaped curve. It has a peak in the middle, and it tails down off to the left side and off to the right side. Technically, those tails keep going forever. They go out to positive infinity on the right and negative infinity on the left. But the probability of getting that far away is vanishingly small. This normal distribution has a mean, it has a center at 5, and it has a standard deviation equal to 2, just to show you what that looks like. So I'll copy and drop that into the notes. All right, so there are a series of questions we can ask with normal distributions, and they kind of relate to those questions we asked about binomial distributions in the previous week's lecture. One question could just be, what is the expected value of a normal distribution, i.e., what is the mean, and what is the standard deviation? We can ask, what is the probability of observing a value between two, I'm going to say observing an outcome between two values, or greater than a value or less than a value. We can talk about percentiles from normal distributions. And we can ask questions like, how likely is it to observe a value more than 2 standard deviations away from the mean, which is a very common question. And if someone claims that, no, I'll save that for a later question. So these are some of the questions we can ask about a normal distribution. So first of all, the mean of a normal distribution is the value directly underneath the central peak. The mean equals the median in a normal distribution. The standard deviation of a normal distribution is not something that we calculate mathematically. It is usually given to us, or we estimate it from data. So I don't have a formula for the standard deviation of a general normal distribution. We have one for a general uniform distribution, right here, max over min divided by square root 12 is for a uniform distribution, but we don't have a formula for a general normal distribution. There's a special kind of normal distribution called the standard normal distribution, has a mean equal to 0 and a standard deviation equal to 1. So if we come over here to our normal distributions and I change that to a 0 and I change that to a 1, we have our standard normal distribution. And I'll drop this in here. The center is right at 0, and the standard deviation is 1 to either side. So 95% of the area under the curve about 95% of the area under the curve is within 2 standard deviations of the mean. If you remember back to 2 weeks ago, we talked about how 2 standard deviations for a data set tells us the kind of the cutoff for extreme values. It's very similar to this here. 2 standard deviations away, so -2 up to +2, 95% of the data is between those 2 bounds, leaving only 5% outside of them, or 2.5% in the left tail and 2.5% in the right tail. So let me show you that. So I can calculate the area between 2 values. And if I put -2 up to +2, and I calculate the area, I get just about 95%. There. Which means that outside of this region, we have just about 5%. And in any given tail, let's look at the right of a value, we have about 2.5%. It's actually 2.28%. If I want to get a little more specific, I can put 1.96 and we get 2.5. But 1.96 is very close to 2. So the area to the right, greater than 2 standard deviations above the mean, is very close to 2.5%, just like the area less than 2 standard deviations below the mean. Recall from chapter 2 that the the z-score of an observation counts how many standard deviations above or below the mean that observation is. So for example, suppose we have a standard normal distribution so that the mean is 0 and the standard deviation is 1. An observation that equals 1.7 is 1.7 standard deviations above the mean. If instead we have a normal distribution whose mean is, let's say, 17 and standard deviation is 4.3, we can still calculate how far or how many standard deviations above or below the mean an observation is, using the same formula that we did before. So let's say that x is 26. Then we can do 26 minus the mean divided by the standard deviation, and we get 2.93. So our interpretation is that the observation x equals 26 is 2.093 standard deviations above the mean. One of the nice things about R is it allows us to quickly calculate these different values. So I'm going to hop over here to R and show you how to calculate the z-scores, calculate how many standard deviations above or below the mean an observation might be. All right, so let's use our example where we had a normal distribution. Mean is 17, standard deviation is 4.3, and my observation x equals 26. So we'll use that simple arithmetic again. The z-score for x is going to be 26 minus 17 over 4.3. And we see that the z-score is 2.093. Well, just like with the uniform distribution, we often want to know what is the probability of observing a value that's greater than x equals 26. This is the area under the curve that is to the right of 26. So if we look over here at our normal distribution, we can put a 17 for the mean and a 4.3 for the standard deviation. And here's our normal distribution, standard at 17. And now we can calculate the area to the right of 26. And it's going to give us 1.82%, or 0.0182. We can do the same thing in R using the command qnorm, pnorm, where we put in our observation, 26, we put in our mean, 17, and we put in our standard deviation, 4.3, and now we have to tell it we want the lower dot tail equals false, and it will give us the upper tail. So if I enter that, I get the probability 0.018, which is exactly the same as the probability I got here, 0.018. So this is how you find the area under the curve that is to the right of 26, or the probability of observing a value greater than 26. I could ask, what is the probability of observing a value smaller than x equals 14? So here I would do p-norm. I'm looking for 14. The mean is 17. The standard deviation is 4.3. And I'm looking for values smaller, so I want the lower tail equals true. Let me put this. And when I run that code, I see the probability of observing a value smaller than x equals 14 is 0.24. About a quarter of the time, I would expect observations to be less than 14. And I could ask, what is the probability of an observation between x equals, let's say 12 and x equals 22? There's no one single code here, but what we're going to do is we're going to turn this into the probability that x is less than 12 and the probability that x is less than 22, and then we're going to subtract them. So we do p-norm, 12, 17, 4.3, lower tail equals true. P-norm, 22, 17, 4.3, lower tail equals true. And then we take the larger value and we subtract the smaller value, and we get a probability that's equal to 0.755. Let me show you what I mean with the graph. And as a reminder, like I said in the uniform distribution video, graphs are a super helpful way to understand these probabilities. So here's my distribution, and I'm looking for the area between two values, between 12 on the left and 22 on the right. Calculate that area, I get 75% or 0.75. just like I did here, 0.75. Now, in R, it doesn't calculate the area between two values. It just calculates the area to the left of a value. So first, we look at a value left of 22. And then we're going to take away from that the value less than 12. And what it leaves is the values between 12 and 22. So this code will allow you to answer a lot of your homework questions. You can also imagine how you could find what is the probability of observing a value more extreme than x equals 20. Well, this means the probability of observing something greater than 20, or looking for something that's going to be, in this case, 20 is 3 more than 17. So observing something more extreme than 3 less than 17. And so we would take p norm of 20, 17, 4.3. We want greater than, so we're going to do lower tail equals false. And we add to that the probability of observing something less than 14. And we get 0.485. 0.485, and here in this app, and I'm going to put a link to this in the weeks module, you can actually do outside a region. So it's going to be, what was it, less than 14 or more than 20. Calculate the area. There it is, 0.485 or 48.5%. All right, let me copy this code. They're using R to calculate probabilities about normal distributions. And what was our other question? How likely is it to observe a value more than 2 standard deviations away? Actually, we did that. That's good. Percentiles. Okay. To calculate a percentile in a normal distribution is to ask, what is the cutoff for a given percentage of the observations? So let me show you using this applet. You can actually calculate a value corresponding to an area, which is exactly what a percentile is. So using our same mean equals 17, standard deviation equals 4.3, I could ask, what is the value that is greater than 30% of the observations? Which is the same as saying, what is the 30th percentile of this distribution? Now, with a uniform distribution, we had a simple arithmetic way to calculate that. You just took the max minus the min times your percentile and added the min. There is no simple calculation to do that with a normal distribution, which is why we use tools like this applet or like R. In the applet, I would say, okay, I have an area and I want to be greater than 30% of my observations. So I want the boundary values for the left tail to have an area of 30%. Oops, let's try 0.3. 30% is a decimal. And it shows me that my cutoff for 30% is 14.745. And that's about 0.52 standard deviations below the mean. So that's how you do it with the applet. You put in your mean, your standard deviation. You choose calculate a value corresponding to an area. You put your percentile as a decimal in, and then you calculate the values. I'm actually going to do this with the labels on the plot. I like that. And there we go. And to do this in R, it's very similar. Using R to calculate percentiles from a normal distribution. Mean is 17, standard deviation is 4.3. Calculate 30th percentile. So here we use Q norm, and we're going to use 0.3 or 0.3 as our probability or percentile. The mean is 17, the standard deviation is 4.3. Since we're doing a percentile, we want lower tail equals true, so we can leave that alone. And when you run that, there we go, 14.75, just like we found here, 14.745. 14.745. All right, put that there. Okay. All right, that wraps up the content for normal distributions. Your homework questions has some conceptual questions about normal distributions, and then it asks you to dig in and use this information to calculate some normal distributions and characteristics. I'm going to do one of those questions for you so you can see how I use the applet and how I use R to answer those questions. So open up my open math. It is chapter 5, normal distribution. And I'm going to hop down here to, let's look at question 16. Your numbers may be slightly different. So the weight of seedless watermelons is normally distributed with a mean of 6 kilograms and a standard deviation of 1.7. And so we can put the mean here for 6 and the standard deviation there for 1.7. What is the median seedless watermelon weight? Well, remember the mean and the median are the same, so 6. What is the z-score for a seedless watermelon measuring 7.4 kilograms? So I'm going to come over here to R, and I'm going to use the formula that says I take my observation, which was 7.4. I subtract the mean, which is 6, and I divide by the standard deviation, which is 1.7. And I get that the z-score is 0.823, which means it's 0.8 standard deviations above the mean. Accurate to at least 4 decimal places. I'm pretty confident that I'll be good if I do this. What's the probability that a randomly selected watermelon will weigh more than 5.8 kilograms? So I'm going to answer this 2 ways. I'm going to answer it using R, and then I'm going to answer it using the Stapplet. So to answer it using R, I want the probability that X is greater than 5.8, given a normal distribution of 6 and 1.7. And so I use P norm. Was it greater than? Let me double check. Yep, greater than 5.8 kilograms. 5.8, 6, 1.7. Mean equals 6, standard deviation equals 1.7. And since I want it greater than, I don't want to take the lower tail, so I write lower tail equals false, and I get a 0.5468 probability. And that can go right in here, and I'll get it accurate to 4 decimals. Now I'm going to use the applet to answer the same question. I come over to the applet, I put in my mean of 6, my standard deviation of 1.7. I'm going to find an area under the curve, something greater than, I believe it was 5.4, 5.8. And I calculate the area. This gives me a percentage, 54.68%. I have to convert that to a decimal, which is 0.5468. So if you're going to use the applet, make sure you convert the percentages to decimals. What's the probability that a randomly selected seedless watermelon will weigh between 5.2 and 6.2 kilograms? So again, I can do this with the applet or with R. I'll do it with R first. So I've got the probability that X is between 5.2 and 6.2. 5.2 and 6.2. So that's like saying X should be less than 6.2. Take away the probability that X is less than 5.2. And since it's less for both, I can leave lower t equals true, and I get 0.2779. Be careful when you're rounding. I've been able to truncate those because of the way it rounded, but if I'm going to truncate this one, I have to round up to 0.2279. And I can do that using the applet. Now I'm going to calculate the area between two values, 5.2 here, 6.2 there. Calculate that area, 22.79% or 0.2279. Get the same answer either way. And the 70th percentile for the weight of seedless watermelons. Using R, I can look at the 70th percentile. So I'm going to do Q norm, 0.7, still 6 and 1.7. And I want lower tail because it's percentile. And I get 6.891481. And if I do it in the app, I change to calculate a value corresponding to an area, calculate boundary values for left tail for an area of 0.73. And there you go, 6.891. Something to keep in mind is this applet may not give you enough precision, 6.891. It's going to be okay here, but well, I don't even know if it's going to be okay. Let's try it. Yeah, it was close enough, so they accepted it. And that's how you would approach these types of questions. There's a couple different ones like this, and you just have to identify what's your distribution and then work through the different questions. All right, that concludes this video. There'll be one more video for chapter 2, or sorry, one more video for chapter 5. So I'll see you in a bit.